Hey everyone, this is Juan Ramirez with EE2725 Linear Circuits 3AC, and today we're going to cover the effective or RMS way of representing a voltage or current value. RMS stands for root mean squared, and that'll kind of make sense shortly. But essentially the RMS value, which is what I'll use to refer to this value type. We use that for calculations of power and also heating. So oftentimes when we have a sinusoidal current, we'll use that sinusoidal current converted to a RMS value and then square that and multiply by the impedance of a wire, and that's how we can determine how much power is dissipated as heat through that wire. So we use that for wire sizing. So that's one application of RMS. But we tend to use RMS just kind of across the board for sinusoids specifically. And a perfect example of that is the voltage that you get from your wall outlets, which are 120 volt RMS. And we've used several examples in the class before where we see the peak value is 169 volts or so, but the RMS value is about 120 volt. You'll also have, sometimes you'll see people refer to it as 110 volts RMS, and that's because the voltage actually varies quite a bit. So it could be anywhere from 110 to 130, but 120 volts is nominal. So in the US, you'll typically get 240 volts from the transformer right outside your house. We call it a pole transformer. Converts three-phase higher voltages, so maybe right around 7 kilovolts or something along those lines. It'll convert it to single phase 240 volt, and then it'll have a center tap, and that center tap allows you to have two different 120 volt lines relative to some middle point, which we call neutral, and we also connect to ground. So that's sort of the actual application in our everyday lives. So let's get started here. When dealing with sinusoids, we commonly use the RMS value. And specifically, we do that of the voltage and current. So there isn't really an RMS value for power. We just refer to that as average power, as we'll see shortly. So this is a common way of expressing these values. And how do you actually find the RMS value? So RMS is a constant value for a steady state voltage or current. So obviously the voltage and the current is time varying, so the instantaneous value is varying with time, but the RMS is sort of like the equivalent to the peak value in that they don't change, right? The amplitude of the sinusoid is constant if you have a steady state voltage or current. In the same way, the RMS value is constant. Not to confuse the RMS value for the amplitude, they're different, but they don't vary with time unless the AC signal is not steady state. So the way to find the RMS value, and I'm going to use X as a general variable. So instead of voltage or current, I'm just going to say X. That is our equation to find the RMS value of X of t. So if you have some voltage or current signal, and you want to find the RMS value, you take 1 over the period and multiply it by the integral from 0 to period t of that signal squared with respect to t. And then you take the square root. And that's why it's the root mean square. So root because you have a square root, mean because you have that 1 over t times the integral from 0 to t, kind of like we saw for average power, and then squared because obviously we're squaring the signal. Okay, so that's RMS. And we're going to do a few examples, and I think that'll kind of show how we apply this, how we find the RMS value, and also some of the applications of it. And I'm kind of OCD, so that was bothering me. Not that much better, but okay. All right, so first example. Okay, so say you're giving this signal, right? It's a DC signal that's periodic. It's DC because the current is not going negative. It's always positive. In this case, positive 10 amps or no current at all. So technically it's DC. And we want to find the RMS value of the current, this time varying DC current. So the first thing we're going to do is we're going to find a time domain representation of this signal. For that, we're going to create a piecewise function. We realize that the value of the signal is 10 amps from 0 to 0.5 milliseconds. And then the value of the current is 0 from 0.5 to 1 millisecond. And it's pretty clear that the period is going to be 1 millisecond. Right? So after 1 millisecond, it repeats that same pattern. Okay, so now we want to find the RMS value. So what I'm going to do is I'm going to plug in what we know into that formula. So that formula said 1 over t. Well, what's t? T is 1 millisecond, or 0.001. So then it'll be multiplied by the integral from 0 to t. And the integral will be of the current squared. Well, clearly, the current is piecewise, and therefore we're going to have to split it up into both parts of the piecewise function. Okay, so from 0 to 0.5 milliseconds, the value was 10. And we have to square that. And from 0.5 milliseconds to 1 millisecond, the value was 0. Okay, so it's pretty clear that the integral of 0 is 0, so that right term approaches 0. And then the left term will look like this. Okay, so 10 squared will be 100, and then you integrate that, you get 100t from 0 to 0.5 milliseconds, and that's all multiplied by 1,000. All right, well, then we just work that out, so it'll be 1,000 times 100 times 0.0005 minus 100 times 0. And that should then give you square root of 50, which is equal to 7.07 amps RMS. Okay, so that's the RMS value of the current, which is somewhere around here. And so that RMS value would be the one that we use to size the wire carrying this pulse waveform, right? We have these 10 amp pulses. If you recall from the transient circuits course, we spoke a little bit about duty cycle. So here the duty cycle would be 50%, because 50% of the time the pulse is on or high, and the other 50% of the time it's low or off, no current. And so with a 50% duty cycle, the RMS value would be 7.07 amps. In fact, there's a formula for the duty cycle, the RMS value using a duty cycle. So for pulse waveforms, we're going to create sort of a general formula. And that formula, I'll give it to you as a current, let's say. And so that current will be equal to the peak value, which we use IM for. And that'll be multiplying by the square root of the duty cycle. Okay, so the duty cycle in this case was 0.5, right? So let's see. Let's see if this is true. The peak value is 10 amps. And the duty cycle was 0.5. Right? 0.5 is the same as 1 over 2. So this is the same as 10 divided by square root of 2. And that'll give you 7.07 amps. All right. So that's how we go about finding the RMS value for pulse waveforms. Now let's do another example. Example 2, we're going to look for the RMS value of sinusoidal voltage. In this case, I give you the actual equation instead of the graph, so you can see it in both ways. If you have a graph, try to find the equation that represents it and use that to find the RMS value. So we want to find the RMS value of this voltage. Okay, so to find RMS value, you're always going to need the period. And if we recall, omega is the angular frequency is equal to 2 pi f. And therefore, omega is equal to 2 pi over t. So if you solve for t is equal to 2 pi over omega. And omega is 377. So the period is about 16.7 milliseconds. Okay, so now let's plug it into our formula. Okay, so square root of 1 over the period, integral from 0 to the period, times the signal squared. Okay, and then after that it just kind of becomes a math problem. So we're going to square this. So the square you can apply to the 169 and to the cosine separately. Alright, and then 169 squared multiplied by the 60. And you get some pretty big number. 1,713,660. And now I'm left with the cosine squared of 377t, but I could use one of my trig identities to simplify that into 1/2 times 1 plus cosine 2 times the original angle. Okay. So the cosine squared, that's an identity I definitely encourage you to remember. Especially when finding RMS value. Okay. And we continue to elaborate. I'm going to distribute, or rather multiply the 1,713,660 by the half to get rid of that. And then I'll split up the 1 and the cosine of 2 times 377t. Split those up, integrate them separately, and go from there. So Okay. And then we evaluate the integral. Integral of cosine is sine. And of course we have to apply the chain rule. So it's 1 over the argument of cosine times the integral of cosine. And then we evaluate it further. One over 754 is 0.0013, and then we insert that argument for sine. But both of those go to 0. So what you end up with is square root of 856, 830 times your 0.0167, and that gives you about 120 volts. Okay. So pretty much what I ended up, or what I had mentioned before, if you have an amplitude of 169 volts, you end up with an RMS value of about 120 volts. And that's the situation we have for power systems in the US, mainly residential power systems. When you go into industrial, you typically have 120, 208. They use 3-phase. And then the other standard is 277, 480. So the 120, 208, 120 is a line to neutral voltage, 208 volts is the line to line voltage for 3-phase. And then the 277, 480, 277 is line to neutral, 480 is line to line. If you take a power systems class, you'll learn all about 3-phase. So what I was going to kind of summarize is that the RMS value of voltage is 120 volts in the US. The peak value of that voltage is about 169 volts. The frequency we know is about 60 hertz. In many other places in the world, it's 50 hertz. The angular frequency is 2 pi times the linear frequency, 377 radians per second. So if I wake you up in the middle of the night, you should right off the bat know these values. Hopefully a key takeaway for from this class. So I will ask you to make a note or to realize something, and it's that 120 volts is equal to 169 divided by square root of 2. And so if you were to maybe redo this exercise but use sort of variables instead of real numbers, what you find out is that for a pure sinusoid, the RMS value is equal to the peak value divided by square root of 2. Okay. And so that's for a pure sinusoid. And that's regardless of phase. So if you have a non-zero phase, this is still true. Okay, so that's another sort of shorthand RMS calculation. So we know for a pulse waveform with a known duty cycle, we know the RMS value, and now we also know the RMS value for a pure sinusoid, or at least a shorthand calculation. Now let's do one last example. What if we have a signal that is sinusoidal in nature, but it has a DC offset? All right, let's say the DC offset is 10. And the peak voltage is 20 volts on the high end and 0 on the low end. And then for simplicity, we'll make the period equal to 1 second. So this signal, which we'll call x of t, kind of keep it general. What if we want to write this signal out? So the signal, the sinusoidal portion of it, has an amplitude of 10, right? And in fact, this follows sine, not cosine, or cosine with a phase shift. So let's just write it as a sine for now. And the argument is 2 pi, right? Because the coefficient before t will be omega, the angular frequency, which is 2 pi f. In this case, f is equal to 1. Period is equal to 1, and therefore f is equal to 1 over the period, which is 1 hertz. Okay, now how about the DC offset? The DC offset is simply a constant adding to that sinusoid. Okay, so this is the actual signal that we will now try to find the RMS value for. And it's not very uncommon to find or have a sinusoidal signal with a DC offset. So in fact, a lot of times in measurement systems, we have our signals all in DC. We all want them to be positive, because a lot of times we only have positive DC voltage relative to some point we call ground or reference. But maybe we're measuring an AC signal or an AC value. So we'll intentionally add an offset and scale it so that our measurement system could read it. And then once we do any type of signal filtering, conditioning, that signal will go into an analog to digital converter typically, and the output of that analog to digital converter will go to a microcontroller. And in the microcontroller code, you will account for that offset and the scaling. That's a typical technique we use. Okay, so now let's find the RMS value. So 1 over the period is 1. Integral from 0 to the period. And then we square the signal, and then of course integrate with respect to time. So when you square that signal, you can FOIL it out. Okay. So far, so good. Next, so integrating the 100 and the 200 sine 2 pi t. Not too difficult. Now for the sine squared, we're going to again have to use that trig identity to convert it from a sine squared to cosine of 2 times the argument. So what I'm going to do is I'm going to split up these integrals into each of the terms. Okay. So the sine squared of theta is equal to 1/2 times 1 minus cosine of 2 theta. As opposed to for the cosine squared, it was 1/2 times 1 plus cosine 2 theta. Okay. And now we evaluate. That's right. All right, so now we did the integral of 100 is 100t, integral of 200 sine 2 pi t is 200 divided by the 2 pi times negative cosine of 2 pi t. And the integral of 100 over 2 times 1 is 50t. And the integral of negative 50 cosine of 4 pi t is going to be 50 over 4 pi times, I guess technically it'd be times negative sine. There's going to be minus sine of 4 pi t. Okay. And so we end up with 100 times 1 minus 0 plus 100 over pi times negative cosine of 2 pi plus cosine of 0. Cosine of 2 pi is 1. Cosine of 0 is 1. So this whole thing approaches 100 over pi times negative 1 plus 1, so approaches 0. Right? Then we end up with our 50t. So 50t will be 50 minus 0. And we end up with 50 over 4 pi, which is going to be 3.98. sorry, that's minus 3.98 times sine of 4 pi minus sine of 0. Sine of 4 pi is 0, sine of 0 is 0. So this whole term goes to 0. And what you end up with is square root of 100 plus 50. Okay, and our value, final value, is 12.25. That's the RMS value for this sinusoid with a DC offset. Now, let's make a couple of observations. The DC component was 10. The amplitude of the AC component, or let's just say the AC component, was 10 sine of 2 pi t. The RMS value of the DC component, if we were to do it the way it is, if you were to find the RMS of just the DC component, the RMS value would be equal to 10, which is equal to square root of 100. For a constant DC voltage or current, the RMS is the DC voltage or current. And if you are to go through the exercise of putting it into the calculation, you'll find that out. And so the RMS value of the AC component will be 7.07, which is 10 divided by square root of 2. Again, based on that shorthand calculation of the RMS value of a pure sinusoid. And that's actually equal to square root of 50. Well, did we notice that we have this over here? We have the DC component of the RMS and the AC component of the RMS, both in that final step of the calculation. It turns out that a signal that is sinusoidal and potentially includes a DC component, that signal can be represented in RMS form with a shorthand calculation the way we've seen for the others. Let me show you what that looks like. So if you have a current signal, and this of course goes for voltage signals as well, and it has, let's say, a DC component, and then it has an AC component, I1 cosine of omega 1t plus phi 1. And then maybe it has even another AC component at a different frequency. And could be different amplitude, different phase angle. The RMS value of this is equal to square root of the square of each RMS value. Okay, so that's again the shorthand form of calculating RMS value of a sinusoidal signal that could have multiple frequency components, including the DC. Technically, DC has a frequency of 0. Okay, and so those are the 3 main kind of tricks to finding an RMS value quickly. So again, that's for a pulse waveform, a pure sinusoid, and a sinusoidal signal with multiple frequency components. This is especially important in power systems. You'll end up finding, as you get into more advanced power system analysis, that the power we get is not purely sinusoidal to, at one frequency. It'll oftentimes have some frequency content or some harmonics that have frequency or frequency content at different values. So, what that may mean is you may have a signal that has RMS value of 60 hertz. So that's the ideal case. Again, that would mean the peak voltage would be 169 volts. But in real life, it's not a purely sinusoidal signal with 60 hertz. It'll have some content, and we call it, different harmonic content, or different harmonics. So typically you have third harmonics, fifth harmonics. So the first harmonic is a fundamental frequency. That's a fundamental frequency. That's 60 hertz. But you're also going to have undesired third harmonics, which will be 60 hertz times 3. So that means that this signal, the third harmonic, if we're drawing that separately, it'll have a frequency of 3 times that, right? So right over here, it'll go like this, right? So one period of the first harmonic, or the fundamental, frequency signal, we had 3 times as many cycles of the third harmonic. And then you'll have a fifth harmonic, and so on. Okay, so if you ever hear about the harmonic content of a sinusoid or of a voltage or a current, that's what it means. It means that you don't ever have pure 60 hertz signal with no other harmonic content. You'll have some other harmonic content, and that's due to the way generators work. That's due to non-idealities in the transmission lines. That's due to power electronics that we use to convert from AC to DC, and they put harmonics on the line. So these are some of the more practical applications of AC power systems. All right, so that's maybe a little bit more background than what you need to actually get going on some of these examples and problems, but I definitely encourage you guys to take a stab at a few of them. Sometimes you'll get them in the form of a graph, and you have to first convert that graph into a time domain expression, and then find the RMS value that way. Or if you already have the expression, then you just plug it into that formula. And remember to use those tools that we uncovered for the 3 different cases, which are pulse waveform, a pure sinusoid, and a sinusoid that has different frequency content. All right, thank you very much.